Professor Towns, members of the Society of Sigma Psi, ladies and gentlemen, tonight's presentation is the annual lecture in the sciences sponsored by the Society of Sigma Psi and the University Committee on Public Lectures. We are honored and very pleased to have as our guest speaker one of the most eminent scientific leaders, Professor Charles Towns of the Massachusetts Institute of Technology. He will lecture on interaction of intense light beams with matter. The Society of Sigma Psi comprises members working in all of the domains of the natural sciences, including also applied sciences such as medicine and engineering. It is difficult to think of a more fortunate choice of speaker for this occasion than Professor Towns. His wide interests range far beyond the field of physics, and his work is making an impact on many disciplines, such as the fields of astronomy, biology, medicine, chemistry, engineering, and even indirectly linguistic, in addition to the field of physics. His creation, the laser, is already in use for operation restoring eyesight to victims of retinal detachment without surgery, and an entirely new approach to photography has been created through the process of holography, which relies on the use of lasers, to mention only two of the countless new applications of his ideas. Professor Towns was born in Greenville, South Carolina in 1915. He graduated from high school at the age of 15 and enrolled at Furman University in his native city as an undergraduate. He completed the requirements for a Bachelor of Science degree in physics and for a Bachelor of Arts degree in modern languages, and graduated summa cum laude at the age of 19. Dr. Towns' versatility showed itself early in college. He was fascinated, to use his own words, by the beautifully logical structure of physics, and since his sophomore year, this was the case. At the same time, he pursued the study of modern languages and of natural history. He became curator of the Museum of Furman University and worked during the summers as collector for the Furman's University Biology Camp. Dr. Towns obtained his master's degree in physics at Duke University in 1936 and his PhD at the California Institute of Technology in 1939 with a thesis on isotope separation and nuclear spins. Following his graduation, Professor Towns joined the technical staff of the Bell Telephone Laboratories and worked during the Second World War on design of radar bombing systems. This work guided his interest towards microwaves. He realized their potentialities as a powerful tool for the study of atoms and molecules, and developed highly original and most effective methods for their generation, amplification, and utilization for the solution of many important scientific problems. Professor Towns joined the Columbia University faculty in 1948 and conceived the idea of the maser in 1951. Maser is an abbreviated term, and Professor Towns' preferred complete statement is molecular amplification by stimulated emission of radiation. The story of how the idea of the maser came to Dr. Towns is no less romantic and picturesque than the legend of the Newtonian apple. He was attending a physics meeting in Washington, D.C. in early spring. Being an early riser, he got up quite early, in fact, before the opening hour of the restaurants. He decided to take a walk through Franklin Park to enjoy the sight of azaleas in bloom. And as he sat down on a bench to admire the beauties of nature, the idea of the maser occurred to him. Although Professor Towns was assured by some experts that the idea wouldn't work, he persisted, and in 1954, the first amplification of microwaves by stimulated emission of radiation was achieved. In 1958, Professor Towns and his brother-in-law, Professor Shawlow, demonstrated how to achieve the same result for visible and infrared light through a new scheme which they discussed theoretically. This led to the practical development of lasers, which amplify light by stimulated emission of radiation. To enumerate all of the achievements and all of the important functions and honors of Professor Townes would leave no time for his lecture. I shall therefore confine myself to a greatly abbreviated summary. Professor Townes holds a distinguished professorship at the Massachusetts Institute of Technology, which carries the title of Institute Professor. He resigned this year from his post as provost, in which he shared responsibilities for educational policies and research programs at MIT with the president, in order to devote more time to research. Professor Townes served variously as member, chairman, and trustee on 39 committees and boards, of which I shall mention only the President's Science Advisory Committee, the Strategic Weapons Panel of the Department of Defense, and the trusteeship of the Salk Institute for Biological Research. Professor Townes is a member of the National Academy of Sciences and of 10 scientific societies, of which I shall mention only the American Physical Society and the Biophysical Society, to which he no longer belongs as of this year, but to which he belonged until recently. Professor Townes holds 15 honorary doctorates from American and foreign universities, and he received 12 major scientific awards. The highest recognition was the Nobel Prize for Physics in 1964, which he received for his work in microwave physics and quantum electronics, especially for his invention of the maser and laser. A portion of this prize was shared by two Russian scientists, Prokhorov and Basov, who conceived independently similar ideas shortly after Professor Townes, and published a theoretical discussion of these ideas after Professor Townes' publication revealing the experimental demonstration of the workability of the principle appeared in the Physical Review. It gives me great pleasure to introduce Professor Townes, one of the principal developers of a new science, quantum electronics. Professor Townes.
Thank you very much, Professor Colin. Members of Sigma Psi, it's a pleasure to be here and to wonder at the growth of UCLA and its attractive buildings. I'm sure everybody is wondering why I was boosted out of the Biophysical Society. And let me say it was a financial problem. Too many dues to keep up with. What I want to talk about today, I call what a laser beam does to matter and vice versa. And here I'm talking about intense laser beams. Laser beams have a number of interesting properties. They're first a very pure form of light in being almost monochromatic. Secondly, they are highly directive. But thirdly, and of particular interest tonight, is that they can be very intense. Once one can amplify light, there is no longer any limit as to its intensity, excepting how much energy one can feed in. These lights you see here are incandescent and radiate in a way that's limited by certain thermodynamic principles and black body laws. But if one can amplify, then by successive amplifications, we can get energies which are almost limitless until we can no longer contain them. Now, how much is that? A laser beam can quite easily transmit some billions of watts of power Now, 1 billion watts is about the energy taken by a large city of, say, 1 million inhabitants or something like that. And in a laser beam with a diameter of a millimeter or so across, one can transmit that much power. Of course, it can't last very long, otherwise you'd use up all the energy available in the locality and also overheat the building. So these intense laser beams formed as very short pulses perhaps this long or 5 or 6 times longer, lasting lengths of time from a nanosecond to -9 seconds to perhaps a few tens times that. And in some cases, even very much shorter pulses, we think as short as 10 to the minus 13 seconds, which means that the whole pulse itself is only about a very small fraction of a millimeter in length. But what I shall talk about is a usual variety of intense laser pulses of, say, 10 to the minus 8 seconds duration, which would make them about 3 meters in length. Now, billions of watts can be in these. In fact, there really isn't any limit, but usually we go up to something the order of, let's say, 10 to the 10th watts. And if that is concentrated by a lens, as it can be, this means something like 10 to the 18th watts per square centimeter. And by that time, the electric field, the oscillating electric field in the optical wave, would be as high as about 10 billion volts per centimeter. Now, the trouble with that field is that there isn't any material that can contain it, because long before that, any material that the light passes through will be ionized, the electrons will be pulled off the atoms by it. And so normally one can only work up to, let's say, 10 to the 7th, 10 to the 8th volts per centimeter in the light wave, and this is the range we'll be discussing. And what we might first think of as the interaction between an intense beam and matter is something like what Goldfinger did. These beams are intense enough to burn through any material, to break down air, ionize it. The first slide will show how one can focus just a moderately intense beam in air. It ionizes the air, making this illuminated blob that you see. The next slide shows such a beam traveling across a room, sort of sizzling its way across, and these spots of ionization are formed as it goes along. You can see roughly the dimensions. This is a normal doorway and apparatus, happening to be in the Lebedev Institute in Moscow. Some of my Russian friends made this picture. Now, when such a beam interacts with matter, the problem is a little bit like asking what happens when you throw a tomato against a wall. Almost everything happens, and if you try to describe that by equations and isolate the various types of motion, the behavior, you really have a messy problem. I'm not going to talk about beams which ionize, but ones which are a little less intense and which, fortunately, are somewhat more handleable. To discuss these, I think it's useful to look at it from the point of view of thermodynamics. These beams can represent black body radiation within a certain narrow bandwidth, at least, at a temperature of a source which would have to be something like 10 to the 25th degrees. So if we were to express the effective temperature of these beams, we would say it's 10 to the 20th or 10 to the 30th degrees, and of course enormously hotter than any material through which it's passing. Is that my electronic system? Or? Enormously hotter than anything through which it's passing, so there must be a tendency to have thermodynamic equilibrium, And if the beam then interacted completely with material, it would warm it up some, and you would have this tomato effect of everything happening, and material eventually just warming up. But there are certain motions of the system which tend to take energy out of the beam first. They become unstable, they build up exponentially, and so the energy is bled out of the beam quite rapidly into certain specific motions. And if we can isolate those, then we have a reasonably handleable situation. Now, these motions are generated in much the same way as a reed is made to vibrate. As the wind is passing past a reed, there's nonlinear interactions that one might call parametric interactions. The reed begins to oscillate. The wind is somewhat deflected, and so you have a scattering of the air as it passes past the reed, and the reed begins to vibrate and sing. It's unstable. It builds up the vibration, which eventually is limited by the amount of energy available, perhaps still other sorts of effects. And so as the intense beam passes through matter, the matter becomes alive. It oscillates and vibrates in a wide number of different ways and scatters the light, affects it, changes it, and some motions start occurring first and build up exponentially. And as one increases the intensity of light, still others come into play and build up, and you have still other tones that are generated in the system, and it's these that I want to discuss. Now, the next slide shows the only bit of mathematics I'm going to impose on you, the general equations for a simple parametric oscillation. If that can be focused, maybe we can see it. Up here is the equation of a simple harmonic oscillator with some resistive loss, a spring constant, and a driving force. Can that be focused? Well, I guess not. A driving force here, which is associated with nonlinearity, and we will talk about three different sinusoidal motions. One is an incident light wave. Which is fixed and very large, and we call x here, an amplitude x0. Another one is a scattered light wave, which we'll describe by, let's say, x1 here, and this is its equation of motion. And then there is still another kind of motion or vibration, which might be mechanical, it might be light, it might be anything, which we'll describe by x2. Now, these are connected together by nonlinear terms, so that there's a driving force proportional to the intense light and to the coordinate of the other motion. And similarly, this one is connected with the coordinate of this motion. If one looks for solutions to these equations by saying, well, there are these coordinates vary sinusoidally and either build up or decay exponentially together, we substitute such forms of solutions into these equations, we can get a condition for an exponential buildup, which is just the threshold condition where the intensity of the initial wave must come up to this threshold before the other two waves of motions begin to build up. And that's given by this expression. The intensity depends on the damping or resistive losses in these two motions, and it depends inversely on the strength of the coupling between the two motions. So now that's the general behavior which describes a lot of the phenomena that one sees. The first phenomena of this type that I would like to mention is associated with the Raman effect, and one can represent that as a molecule, thank you, made of two atoms and an interatomic distance. And as we put it in an electric field, E, there's an energy, W, is equal to 1/2 times the polarizability times E squared. Now, this is the polarizability of the molecule. And there's a force tending to stretch or contract the molecule, which is the derivative of the energy with respect to the coordinate of the molecule, and this is 1/2 E squared times the change in polarizability as the molecule stretches. Now, this is the coupling term, because in E squared we have the square of the initial field E0 plus another scattered field E1. We square this, and there are terms E0 squared plus 2 E0 E1. When multiplied by this coupling constant, this gives us then a driving force proportional to the intense light wave into a weaker scattered wave. And that's the coupling term that comes into those equations. Now, if we have a number of molecules in the material, perhaps randomly oriented, perhaps all aligned with crystalline material, we send a beam of light through the material. When we reach the threshold condition, the molecules will begin to sing, just like the reed sings. And they vibrate synchronously, all in phase with each other. And so the whole material is vibrating synchronously, and at frequencies which correspond to molecular vibrations or infrared vibrations, enormously high by ordinary acoustic standards at least, maybe 10 to the 12th, 10 to the 13th cycles per second. The next slide shows what one might see if we could look inside of material through which these two beams are passing. Here is a laser light passing through the material. These are the molecules. And if the laser light is sufficiently intense, that is past this threshold, then there is a scattered Raman wave, which is shifted in frequency from the laser light by just the molecular vibrational frequency, shifted down in frequency. And now, if we look at the molecules, we find a whole row of molecules all lined up, stretched at the same time, and the next layer, a whole row of molecules contracted, next layer, a whole row of molecules stretched, and they are all vibrating in phase in such an array, assuming that we have one scattered light beam, one incident beam, one scattered light beam. They're all vibrating in phase and vibrating by an amount which can be considerable if the light intensity is large. In fact, about 1/10,000th of the total dimensions of the molecule. Now, the threshold for this is quite easy to obtain. The threshold power in the laser beam is something like a megawatt per square centimeter, and that's trivial compared with the numbers that I've been mentioning. Very easy to obtain. And so we simply send an intense laser beam through a liquid or a crystalline solid, and we can generate the Raman light and get these molecules all singing synchronously. And now you recognize that we have built into the material, no, I want the last slide back again, please. Built into the material, we have a three-dimensional grating, very much like crystalline layers, let's say, but a three-dimensional grating which is varying in time, so that if any other light wave strikes this three-dimensional grating, may we have the last slide, the previous slide back again, please? No. The previous slide. If any other light wave strikes this three-dimensional grating, it will come off at angles given by the grating formula, or if you like, by the Bragg scattering formula. It will come off at a specific angle, but various frequencies will come off because this light will be modulated by the oscillating molecules, and so we'll have side bands of frequencies, some higher in frequency and some lower in frequency. In fact, one can observe 6 or 8 side bands on either side if you look closely, although no one has checked these in the low frequency direction quite that far. Now to show the specific directions at which some of the light comes off because of this grating effect, the next slide shows an experimental arrangement. One starts out with a laser. This is a ruby laser involving a high-intensity flash tube surrounding a ruby. This is a type which is Lehman's first laser and the very first laser invented. A flash tube around a ruby, and when one flashes it, out comes a pulse of light, and through some material like a cell of liquid, and then the light is scattered, modified in frequency and scattered, and one projects it on some photographic plate. And the next slide shows one of the kinds of results. If we may have the next slide, and I suggest you dim the lights, please. Here is original ruby light beam. Here is one ring of scattering of a slightly lower frequency. If the color film were properly sensitive, there would be a yellow ring right in here. Slightly higher frequency, I'm sorry, is this red ring. A yellow ring right in here, which is still higher frequency. Then there's a green ring, which is a still higher frequency. And we could go on out if we had a slightly more intense beam and sensitive film, to successively larger and larger rings. Now the size of these rings is a property of the individual material and its indices of refraction. And in addition, a property of the frequency of the molecules. The next slide shows another variation on the same theme. Very beautiful designs. The next slide will show that there are also some complications. As one goes up in intensity, all sorts of things begin to happen. You see there is a continuous variation in frequencies, the various overlapping of frequencies. They're no longer rings, they are sort of smears, or they're pairs of rings where one would think there should be one. And in fact, what we see here is rather puzzling. Also puzzling is the rate at which this scattered light builds up, or the rate at which the molecules begin to sing, because they do it rather more readily than one might expect. The next slide shows a curve indicating the intensity of the light and the rate at which the Raman effect builds up, or the molecules begin to vibrate. The scattered light is more or less proportional intensity until we come to here where there should be an instability somewhere, but the instability comes too soon. It's very sudden. Suddenly, the intensity of the scattered light, intensity of molecular motion, shoots up until it uses up almost all of the light that strikes the material, and this light gets scattered out in various directions at various frequencies. Now that was quite a puzzle for a while, and I'll come back to what we think is going on. But next on to another kind of motion, another way in which the material comes alive. Let me remind you now that this is simply passage of light through transparent optical material. We've been dealing with that for many years, but the intensities of the light has been so low that we could treat the material as passive. And so we have all the usual lens phenomena and prism phenomena simply associated with indices of refraction of the material. The material is static and passive. The light goes through it, and we know what comes out. In this case, the light is intense enough that the material really comes alive, and all these various motions in the material occur. They in turn modify the light. The light then modifies the material some more, and we have a series of rather fancy effects. The next effect I would like to mention is simply an acoustic sound wave generated in the material. In addition to molecular vibrations, they are very high frequency acoustic waves associated with what's known as Brillouin scattering. Now, the next slide shows a simple model of Brillouin scattering. If we have an acoustic wave traveling through the material, here are the various wave fronts. When the material is compressed along this wave front, that increases its index of refraction. Here is the next wave front with an increased index, and so on. Now that too is a grating which will reflect light at a certain angle, but it's a moving grating because it's a traveling wave. It's a moving grating, and hence there's a Doppler effect and a shift in the light frequency of delta nu, given by this expression, dependent on the original light frequency, on the ratio of sound velocity to the velocity of light, and on this angle at which the light is scattered. That's one model. Physicists tend to like to think these days in terms of another model, which the next slide indicates, of one photon here, light particle, striking a phonon, which is a sound particle, and being scattered. And one has a conservation of energy, which says that the sum of this frequency plus that frequency has to equal to that frequency, and a conservation of momentum, which says that the wave vectors of the number of loops in this per centimeter have to add up properly, and that's this equation here for conservation of momentum, and from that one gets, of course, the same kinds of results. This type of motion, too, begins to build up exponentially at a certain threshold of intensity. So the material vibrates. It vibrates at a supersonic frequency. In fact, frequencies up to about 6 times 10 to the 11th cycles per second, acoustic waves. These are hypersonic waves. And from that range on down to lower and lower frequencies. And one can generate this way very intense acoustic waves in almost any material. The threshold required is a little higher than the last threshold. Usually it's perhaps 10 megawatts or 1,000 megawatts, but still in a very easy range to achieve. The next slide shows how one observes this spectroscopically to see that it's going on. We have the original ruby light, which in a spectrometer, so-called Fabry-Perot spectrometer, produces isolated rings like this, which tell us the frequency of the light. Now, if we look at the light after it's passed through the material, there is this same ring that started out, but there are other rings corresponding to slight changes in frequency of the order of 10 to the 10th cycles per second. And in this case, it happens that the light is scattered once with a shift in frequency and twice, and one can keep on going. Multiple processes occur, and we can scatter 30 or 40 or 50 times, each time with a shift of frequency, so as we get the whole picket fence full of frequencies. In the meantime, intense acoustic waves have been set up in the material, and in many cases, in crystals at least, these waves become so intense that they simply pull apart the molecules in the crystal and break the crystal. So much for that. You may think that, well, this finishes the motions in the material. You can have molecules vibrating, or you can have the whole material moving together acoustically, and that's it. However, that's not so. There are other kinds of dynamic processes in materials, such as, for example, small fluctuations which produce Rayleigh scattering. Now, Rayleigh scattering happens when you send light through a material, a gas, a liquid, a solid, but let's take a liquid, and there are small fluctuations in the liquid of the orientations of molecules, of the clumping together of molecules, of molecular excitation, or let's say effective temperature, various sorts of fluctuations, and these vary with time. These fluctuations, too, can begin to sing if the intensity is sufficiently high. One can force them to fluctuate more and more violently. Typically, the fluctuation is a molecular rotation. We have the lights now. If we put this same molecule in an electric field, the molecule will feel a force tending to rotate it and line it up with a molecular field, because it can be polarized by the electric field. There's the electric field here. We accumulate a positive charge there and a negative charge there. That then tends to pull the molecule around. When the molecule gets lined up this way, that increases the dielectric constant of the material, or the index of refraction. And so we have, again, a coupling. The effect is proportional to the square of the electric field, and it's dependent on the difference in the polarizability of the molecule in this direction and in this direction. We'll say this difference difference between two different directions of polarizability. You see it has very much the same form as we had before, and so that motion can be made to dance too. It's not exactly an oscillation. It's a very highly damped oscillation with almost zero frequency, but the molecule can be made to twist back and forth, thus modulating the light, and the molecule can be made to twist more and more violently. The threshold for that is a power which we must send through, power density we must send through the material before it begins to take effect. Is still higher, but again not impossibly high. That's about 1 billion watts per square centimeter. And the next slide shows a picture of the first demonstration of this. This was done, by the way, in the Soviet Union by mentioning work of a number of different groups of people, some our own at MIT. Some has been done at Hughes laboratory here, some at Harvard, some in Paris, and some in Toronto. These are, I think, some of the main groups working in this particular area. This was an effect that was found in the Lebedev Institute. If one looks at scattered light, scattered by these small fluctuations in material, this is the light from a ruby laser at a power level slightly below threshold, before the molecules are forced into this back and forth motion. As they start to move, as one increases the power level, they start to move, and the intensity of the scattering builds up rapidly, particularly on the low frequency side of the scattering. The extent of this will tell us something about how damp the molecule is or how fast it can respond, and gives quite directly the speed of response or relaxation time of the molecule as it rotates in the liquid. Here is another line you see, and its extension to low frequency sides, build-up of very considerable intensity in Rayleigh scattering. Normally, all of these scattering processes are very small. Scattering may be 1 part in a million of the light, something like that, of ordinary light, and a little bit hard to see. In these cases, the molecules are forced to move so violently that one can scatter almost 100% of the light, and this is a large amount of light, getting up into the megawatts of power and plenty to burn your fingers with. Well, now, this is not all of the motions still. One might imagine, for example, chemical reactions going on in the liquid, association of its hydrogen and chlorine ions, which also change the polarizability of the system a little bit. And these have time constants, rates at which they can occur. And so in principle, if one sent intense light through the material, one could force the chemical reaction, the bonds, to make and break quickly. And by examining this smear of response, one could tell how fast these bonds were produced and were broken again, or how fast any kind of very fast chemical reaction takes place. The thresholds for those, normally at least, are still higher, and hence not very easy to isolate. There's still other types of motion, such as the excitation of molecular vibrations within a liquid, which will decay and cool off, and then they heat up again, and those can be forced to go back and forth in principle. So there's still many other types of motions which one might think of. But now I'd like to talk about a little different class, a more macroscopic and gross type of effect, which we call beam trapping. And this comes about because material is a little bit affected by an intense wave. And as a beam goes through the material, the index of refraction inside the beam can be a little different from the index of refraction outside. In fact, if we write the index of refraction of the material and its dependence on the field strength, we would expand it. The initial index, which is a common one ordinarily measured, plus a term which depends on the square of the field, plus higher powers and so on. But let's talk about this one in particular. The sign of that term is usually positive. for rather good general reasons. And so inside of the beam, the index refraction is larger than outside of the beam. And as we increase the intensity, the index refraction inside gets higher and higher. Well, this makes a dielectric waveguide. This is very much like a glass fiber that you know will propagate light down the glass fiber without the light getting out. It's a dielectric waveguide made by the light itself. And so the light sort of produces its own trap. And it can't get out once it forms that trap. It's no longer diffracted, it won't spread, and it can be caught in such a region almost indefinitely small in diameter, and then travel for a very long distance. The general idea behind this, one can illustrate rather quickly, is how one would calculate the threshold required to trap a beam like this in material. The next slide shows this. If here is the beam, which would normally spread by diffraction, an angle theta, it would normally spread out gradually by diffraction, the angle theta being given by the ratio of the wavelength to the diameter of the filament. And one simply has to have a change in index across this boundary sufficiently large so that the critical angle for complete reflection at the boundary is a little greater than the diffraction angle for the beam, and if that's so, then the beam is trapped, and this is a light pipe or waveguide for the beam. If we write down the conditions to fulfill that, we find that the power looks like this. It's dependent on the square of the wavelength. This is just the velocity of light, and you see it's a very simple expression. As long as the power is greater than that, the beam will be trapped. You notice that that expression is independent of the size of the beam. The actual threshold power in many materials is only something like 10 kilowatts. It might be from anywhere from there up to some few megawatts of power typically. Now we require a short wavelength in order to have a low threshold power. And so if we were to go up to radio waves, let's say, well, the power would be entirely too high to achieve. But for light waves with lasers, it's relatively easy. And since the power for trapping is independent of the size of the filament, this filament then can be either large or it can be almost infinitesimal in diameter, and the light still is trapped. The next slide shows a picture of what we think is a fossil track. Light was focused in the glass at this point, and probably the acoustic waves began to build up here and so violently that they cracked the glass. But before that, the light became trapped in a tiny little filament going through here. You see this little track. That track is a few wavelengths of light in diameter, in other words, about 2 microns in diameter, and it extends for many centimeters. Very straight. Now, light ordinarily, of course, would diffract and spread out. If it's in such a thin beam, one couldn't maintain it that smaller diameter, more than a few wavelengths of light along. But here it goes for many centimeters, and a very fine little track. The light has been so concentrated into that small filament that after a time of about 10 to the minus 9 seconds, the glass is fused and melted, and then the whole thing, the whole system sort of blows up. The light no longer gets trapped. The glass explodes in a few places, and the whole game is over. In the meantime, though, the fused glass has left us a fossil track. In the case of liquids, of course, the liquid won't keep any such fossil track for us, but one can photograph these tracks. The next slide shows such a beam looked at perpendicularly. The beam is traveling along here. It's an intense laser beam. And now you can see concentrations of light streaked through here, which must be these trapped, little trapped filaments. These filaments are some fraction of a millimeter in diameter, not quite so small as the other ones that we saw. Now, the next slide shows how one can study these beams in some detail. We send them through a liquid. We put in a little glass plate which will reflect out some of the light. And with a microscope now we focus this point on a film, and so we can see in some detail exactly how the concentration of the light in the beam behaves. First place, we make a fairly intense beam of light with a diameter of the order of a millimeter. And this is what happens to a weak beam as we go along through the path of 10 centimeters or so. The beam stays about the same size. It gets a little weaker perhaps. Somewhat more intense beam starts out 1 millimeter in diameter. It begins to concentrate, gets a little smaller. A much more intense beam concentrates rather quickly and then comes down to this little tiny central focused spot which travels over tens of centimeters. And that's the trapped case which no longer spreads. Now, this light trapping can be looked at as a type of interaction between the acoustic motions of the liquid and the light beam, which, however, is of a high order involving lots of exchanges of energy between the light and the acoustic motions. But it's a little easier to think of it in a somewhat less abstract way as a case of the light beam simply pulling material into it. This makes a more dense region here, which then focuses the light a little bit, pulls more material into this region, makes it still more dense, and focuses it and keeps it in a very small beam. The elementary process actually is something that might be called light by light scattering. As if one has one beam of light here, we send another beam of light through it, then this beam of light scatters that one under certain conditions, even though these may be at the same frequency. Now, ordinarily, one doesn't think of light as scattering itself, particularly if it's the same frequency, because now all of this light has the same index of refraction. And to interact with itself, you'll find that the equations work out so that the light just keeps on going in a straight line. It doesn't change anything. But if we allow for an index of refraction that behaves like this and put in two fields, the initial very intense field here, and then another weak field going through it like that, and we square it, we find, well, I should make a displacement vector D, which is really something like this times E, and so we have this times E, and that's E cubed. And if we expand this, this makes E0 cubed plus 3 E0 squared plus times E1 plus 3 E0 E1 squared and so on. And if E1 is much smaller than E0, we can forget about these things. And now let's look at the ratio of the displacement vector to E0, which tells us how the E0 light, the intense light, will be propagated. Well, that is just E0 squared. That's this term, because when we divide this by E0, it's much smaller than that, and we can forget about it. But if we look at the ratio of D to E1, the less intense wave, we find that that is 3 E0 squared. And so a weak wave of the same frequency has an effective index of refraction which is different from a strong wave. If we add a weak wave to a strong wave, the weak wave really behaves rather differently from the strong one and can be scattered. And now the particular direction it's scattered is just off like this, at an angle just equal to its original angle. The next slide shows such an effect. And this is the elementary process of the type of light deflection which gives self-trapping or self-focusing. We want the next slide now. Here it is. This is the strong beam. This is a weaker beam. It looks stronger here simply because this one was filtered out to make it visible on the film. This is a strong beam. This is a weaker beam. the angle that the two make together is represented by this distance, because this is where they hit a film at some distance. And here is the newly generated scattered beam off at the corresponding angle on the other side. Well, now, what else happens to the light? There are various sorts of spatial perturbations and so on. Another thing that happens to the light, lights please, another thing that happens to the light is that as it travels along, if we send a pulse of light like this, we find, because of this behavior, that the top of the pulse goes more slowly than the bottom of the pulse. Now, if the top goes more slowly than the bottom, what happens pretty soon is that we have a light shock wave, because this catches up with the top, and if the light travels a little distance, it begins to look like that, with a very, very sharp edge, but an edge on the back of the wave. And this is as sharp as the nonlinear response, or this response will allow, which means maybe 10 to the minus 12 seconds or something like that is the time required for that edge to go by. So there's a light shock wave corresponding rather closely to an acoustic shock wave, excepting that the shock is on the back end instead of the front end, which is a normal acoustic wave. Now I would like next to discuss a still stranger phenomenon. We mentioned the trapping of light waves, but we've looked at them only in a somewhat gross way. And if one takes a microscope now and looks very carefully at a beam of light, initially of a constant intensity, and after it's been passed through a liquid, you see that the beam of light breaks up into a less regular form, but in addition it has a number of bright spots in it. These bright spots are only a few wavelengths of light across, something like 5 microns. And this is the original laser light sent through the material. It breaks up into this spotted pattern instead of being a nice regular plain wave. And as it goes, within these filaments or spots, there is generated the Raman scattered light that is changed downward in frequency by the molecules which begin to sing. And this is what the Raman light looks like. It comes through in spots or filaments, in an even more pronounced way. Most of these are almost identical in size and very small. So now you see what we started out as a fairly simple plane wave is broken up in a variety of ways, even down to the dimensions of a few wavelengths of light across, because a plane wave just isn't stable any longer. And furthermore, it's generated new frequencies which travel along with it. The next slide shows, I hope, something else in the light beam, namely that there are dark holes in the light beam. Not only are there bright spots, but there are dark holes. Now, let me see if I can see a good one. You'll see small circular holes about the size of the light spots. I hope you can see one right in there. A little circular dark hole. In other words, there are regions in the beam where the light just avoids. And these two have dimensions of the same order, something like 5 microns. And what's happening there? What we think is happening is that the light, as it travels along, first forms in these little filaments. Then, very quickly, the laser light, which is in these filaments, is translated or converted into a shifted frequency Raman light. It's all used up in the filaments, but furthermore, the molecules are made to sing so violently that their vibrational modes are essentially all used up too, and all of the molecules are excited and vibrating, and because they gain energy so fast, and then they begin to expand, and this sort of excludes the light by a dielectric effect, excludes the light from that region after they've expanded. So first the light is used up and there's no light there, then after that the molecules have expanded and the light can't get in anymore, and these dark holes spot, but these dark spots stay. But as we follow along the light beam, these dark spots then become bright, and other bright spots, which we have seen before in all of the latter part of the beam as it travels through the liquid, is then bright again. Well, now you can perhaps see that the various thresholds that I've mentioned for the Raman effect, that is for the molecular vibrations, for the generation of acoustic waves, these various thresholds are bound to be much affected by the concentration of light in these spots. Remember, those thresholds were dependent on the intensity of light per unit area, and we don't know just what that is unless we look in detail at the light, because we can't start out a light of a given intensity. It always gets concentrated in filaments, and it's this concentration in filaments which suddenly puts us over the threshold for almost everything. That is, we increase the intensity of light steadily and steadily, and then at some point the light drops into these tiny little filaments, very, very concentrated, and at that point we're over the threshold for almost everything to happen. The molecules begin to vibrate, the acoustic waves begin to build up, the Rayleigh scattering starts to occur, and everything happens at once, each affecting the other a bit. But there are still other properties of the filaments, these tiny little filaments, that are interesting. In the first place, they last only a fraction of the total length of the pulse, which I said was only a few meters long. The filaments last not longer than 10 to the minus 10 seconds. The reason they don't last any longer is because the light is so concentrated in these small filaments that the liquid very quickly begins to overheat. It expands and a shock wave goes out, and it takes about 10 to the minus 10 seconds for the shock wave to go out and allow the filament to push its way out and expand, and then sort of relieve the trapping. But before that, the field strengths inside the field strength inside these filaments has gotten up to the region of a few times 10 to the 7th volts per centimeter. That has increased the index of refraction in the material by a good fraction, 10% or 20% or something like that. The index of refraction of the material has been increased. Enormous pressures have built up because of electrostriction, tendency to pull the molecules into the field. So the pressure has increased, the density of the material has gone up by an appreciable amount, and things are happening very powerfully and very fast until the filament then overheats and sort of blows up and disappears. Finally, I'd like to show what some of these filaments look like from the side. The next slide shows that the filaments from the side are striped. Now, what in the world is that? The filament of light traveling through material, a liquid, carbon disulfide, something like this. In this particular case, it's 37 microns in diameter, and it radiates perpendicular to the direction of the light. It radiates these stripes, rather straight. These stripes are only 2 microns thick, 37 microns long. Superficially, they look like they're irregularly spaced. If one examines the light, you find that there is light of the laser frequency, original laser frequency, also light of the Raman frequency, shifted down in frequency by the molecular vibrations. Nothing unusual about that. That's the light that's in there. The next slide shows a smaller filament, only 2 microns in diameter, a trapped filament. And that too that's spotted rather than striped. It's spotted only because it's so small, the microscope can't resolve anything smaller than that. It's about 2 millimeters in diameter, 2 millimeters thick, but spotted. Now, may I have the lights, please? That was the last slide. I'd like to use the lights. Now, what's going on this time? And of course, all of this goes on at the same time if you're not careful. Once the light intensity gets in this general range, why, everything begins to quiver and happen. Well, we decided that probably there's standing waves present. And the light is not only traveling in this direction, we introduce it, let it travel in this direction. The light is not only traveling in that direction, it's also traveling back in this direction. Why? Because it's scattered by Rayleigh scattering. It begins to generate molecular oscillations back and forth here, which scatter the light backwards. And if one looks in the backwards direction, sure enough, the laser light traveling backwards is just as intense as the laser light traveling forward. Now remember, this is just perfectly transparent material, which we're accustomed to dealing with ordinary intensities, and nothing fancy happens. But here, we send the light in, and as much travels backwards as forwards, at least almost as much. So that the light is bouncing back and forth in this filament all the time. It isn't traveling straight through, at least as one gets beyond certain thresholds of intensity. That will set up a standing wave pattern in here, like this, with a separation between these peaks of a half wavelength, which means this fraction of a micron. But that's a lot closer than those stripes we saw, and so that isn't it. However, there is also the other type of light, the Raman light, which goes in this direction, and it goes backwards too, and one can show that it's traveling in both directions as well. And that has a standing wave pattern like this, a little longer in wavelength. And periodically, it coincides with these peaks. And so periodically, there should be particularly intense spots in the filament. And something happens in those intense spots, some other kind of instability and something else that is going on. We think it's probably Rayleigh scattering, which builds up exponentially. So if this is our filament and these are the intense spots, now, light is generated coming out in this direction. As it travels through here, it gets more and more intensity as a result of this Rayleigh effect beginning to sing. It comes out in this direction, comes out in this direction from that spot. Why don't all the spots show up? We can calculate how far apart they should be, and sure enough, if we look at them, we find that every spot does fall on some integral number times this length. Every spot or every stripe is some integral number times this length, which we can calculate from our knowledge of the wavelength of light. Why don't they all show up? Well, the reason is because by this time the light is not so pure. It's a little bit of a smear of frequencies. And what a smear of frequencies will do will give you periodic peaks of intensity, all right, but with little fluctuations in the peaks of those intensities. And because this is a process which builds up exponentially, a relatively small change in intensity will change the intensity of light coming out enormously. Now, all of these effects are, of course, useful in that they tell us something about the response of the liquid. They can tell us something about the state of the liquid, its time constants, how it moves, coupling constants, and so on. This particular effect tells us immediately something that we might have been wondering about in the case of these filaments. How do we know what the dielectric constant in the filament is? How do we know what the index of refraction is? Do we know it's really changed? Well, in the larger filament which you saw, with the stripes in it, we measure where these stripes occur, and they come out integral numbers times our unit length, and just exactly what we calculate. This filament is fairly large. The intensity of the field is not so great that its index of refraction would be changed very much. The smaller filament, on the other hand, has spots in it which are a little closer. And they're closer because the index of refraction has been increased, and so one has a fairly direct measurement of the index of refraction. And we know then that the material has been changed. Its index of refraction is increased by a few tenths, and this means that the molecules in the liquid now have essentially all been lined up. That tells us something further about why the filaments come out to be this particular size. And what happens is this, that as one increases the field, the light is not only trapped, it sort of tends to be, as you go beyond the threshold, it tends to be focused. And if we just allow for this behavior, it would be focused and then refocused and so on. But if we remember that as the light is focused in, the fields become very intense, so that the molecules all become aligned, and the behavior becomes different, and this term no longer can increase anymore. And we find that we can work out what the light should do, and it bounces a few times, and then settles down to a size of filament which will just align some reasonable fraction of the molecules, like a quarter of them, or something like that. And what these tiny little filaments are collapsed, trapped filaments, which always collapse once we get above this slight threshold. Well, they collapse down to the minimum size, where all the molecules are aligned, and the material can no longer respond in quite the same way. Well, now you see one of the effects of being able to operate with light, somewhat different properties, radically different properties, greater intensities, the kinds of complications one gets into, but also the rather great detail with which we can begin to study some of the actions and interactions and frequencies and motions within liquids, with solids, and gases, and the very intense scattering that we get, as compared with a rather feeble scattering that one could have used with ordinary light. At the same time, however, we pay for it with considerable complication, because once the filaments begin to form, these tiny little filaments here, the properties of the material are changed. That's interesting in itself, but it means that all of the things that we might hope to predict, the molecular vibrations, the acoustic behavior, the indices of diffraction, they are all changed too. And so we're dealing with material not in a normal state that we think of it, but under states which themselves have been appreciably modified by the light wave. Well, thank you very much.
Thank you, Professor Towns, for a most interesting and stimulating lecture. In spite of a very heavy schedule and a long day, Professor Towns has very kindly agreed to answer some questions. And it would be simplest if you were to address the questions directly to Professor Towns. And please speak as loudly as you can so everybody can hear the questions.
There's a question back here, yes.
Sir, have you found any polarization phenomena occurring, that is, either preservation or depolarizing of the light that passes through the matter?
Yes. Yes, a number of interesting phenomena of that type. The light, for example, when it's trapped in the very small filaments, cannot travel through these filaments in a linearly polarized state. So as the filaments become smaller and smaller, the light becomes somewhat depolarized, and one can detect this You look only for the perpendicular component of polarization. If you started in at one polarization, you find that some of it comes out in reverse polarization in these tiny filaments. Now, in addition, there are a number of effects we don't understand. In the case of the scattering by the hypersonic waves, one sometimes starts out, if you start out with complete polarization, which you normally do in a laser beam, you sometimes get complete depolarization for the scattered wave, sometimes complete polarization, and these are some of the effects we don't yet know. In other cases, if you start with a crystal, then there are changes in polarization which tend to be more or less predictable. Gases and liquids, there certainly are some depolarization effects and polarization effects which we don't understand. And I'm afraid I've just omitted that additional variable, which certainly is there. Yes?
You talk, sir, of the intense electric waves that are generated. Can you say anything about the magnetic component?
Yes. The magnetic component is there, and of the same intensity in terms of the amount of energy in the magnetic component. I haven't mentioned it because the magnetic field does not interact quite so strongly with matter. And this is simply a simple result that the electron has a charge on it, which allows it to be pulled around, and the molecule can be polarized and so on by an electric field and affected very much more readily than by a magnetic field. In principle, the magnetic field will have its effects too, and there are some cases where they may be important. For example, one class of motions that I haven't mentioned are spin waves that occur in magnetic materials, and these too can be made to self-oscillate as a result of an intense field. So there are some effects one can probably observe associated directly with the magnetic field, but the vast majority of the bigger effects are associated with electric field, and this is why I've concentrated on that. Yes?
This is a rather ignorant question, so you may not be able to give a clear answer, but I've always been puzzled about the formulation in special relativity, which says that the proper time of a photon is zero from the time of emission to the time of absorption. I wonder whether the photons, which are going through such unpleasant nonlinearities, are covered by the same time contraction, whether there is anything except from the point of view of special relativity about those nonlinear effects.
Well, I don't think of anything that's especially unique with respect to special relativity here. The time you're referring to, a path length of a photon, is zero only if it travels through a vacuum. If it travels through dielectric material, which slows it down some, then it has a finite effective time in getting from one place to another. What that means is essentially, if the light goes from one point to another, you can beat it getting there with another light wave that goes through a vacuum, you see. And so you can go to this other place and wait for it to arrive, and you say, aha, it took some time to get there. So whenever there is dielectric material, you have a finite path length of the particle, and I don't think this changes it in any qualitative way. Yes? The communications by laser beams is certainly possible. We know how to do it. It can be done in many ways. And so if anybody wants to do it, you can do it, and it's already been demonstrated. The problem there is not whether it can be done, but is it the most economical and sensible and simplest way to do it in light of all of our other developments. We know how to communicate and send television by many other methods. I would say in the long run, I think it will be better in certain specific cases, but we'll wait for some time, I suspect, because we have such good communication means already. They're well developed and they're reliable, and it'll take a long time to make light beams as good, except in certain special cases. So far as television is concerned, I personally would think that the laser beam would come in rather more quickly and as a rather more unique contribution to television by producing the writing pencil in a television tube. Maybe even a writing pencil which could produce television across the screen this big, let's say, from the back of the room, and in color, because we have a number of different colors that can be produced in a laser beam. That serves a rather more unique function than simply communications where we already have good techniques. I think there was another question back here, yes.
Are there any types of molecules which can independently determine the time dependence of the effect that you said occur simultaneously when laser beam interacts with a material?
Well, there are molecules in which one can determine these all separately, and you don't have to have them going only individually and separately in order to determine them, because if you look at the light, the various effects, even though the effects all occur at once, you can see one kind of motion produces one thing, one property of the light, changes its frequency in such a way. The addition of another motion changes it by some additional amount, but leaves some of the original frequency that was there. So that with careful study, one can separate out the various effects, even though they're all taking place at the same time. Now, there are also various ways of arranging the situation so that you can isolate these different effects and see that they don't occur at one time in most cases. One thing to do, for example, to avoid this self-trapping and focusing effect, or at least the focusing effect, is simply to use a very thin layer of material, so when the light goes through it, it doesn't have time to get focused. Well, there are a variety of tricks that you can use to help isolate the various effects, and I think one can be fairly hopeful of being able to study them individually in quite a variety of materials. At the moment, we're just trying to find out what's going on, and as we started into this, and other people did, there were a few things that seemed fairly simple. We talked about them in terms of plane waves and worked out nice equations and so on. As the situation got more and more complicated, it was easy to wonder, well, is all this necessary? But it becomes more and more interesting as you go on, and of course you have a kind of an obligation to science to really figure out what is going on, because this is now a rather common situation with intense beams. And with careful work and a little luck, you can find ways of isolating them. Eventually, we'll reach the point where ionization occurs at the same time, and the light is all so smeared out that we'll get close to the point where the light is just heating things up. And there, clearly, you'll have to switch over to just a thermodynamic approach, which is again simple. In the intermediate case, where almost everything happens, excepting that they're not yet in any thermodynamic equilibrium, that will be very hard. Yes?
Can you concentrate enough energy in matter by lasers to obtain nuclear fusion?
Well, yes. Yes, and that can be demonstrated. You can't. No one has succeeded, and I think it's exceedingly difficult to concentrate enough energy over a large enough volume so that you could set off a sustained reaction. To demonstrate that you can produce nuclear reactions, that can be done. But to set off anything that's sustained is very much more difficult, because you've got to get a sizable amount of material together and heat it up all at once. Try heating it up this way, it explodes and it's hard to hold together, and in addition to the fact that you have to have a whale of a lot of power. So I wouldn't be too hopeful of its giving us thermonuclear energy or something like that anytime soon. Yes?
Involved with the applications of lasers to oceanographic studies and submarine detection. And one of our problems is not only back but forward scattering of light to try and make optical systems. Do you suppose that with the increasing powers of Q switching and say the liquid neodymium laser that sort of dielectric channel can be formed in seawater?
Yes. One can certainly form a dielectric channel in seawater. I don't think this will help your problem very much because I think the numbers involved just are not going to be very favorable. By the time you get to those intensities to form channels, you will find that in seawater, many of these effects, plus some others, will come in which will sap the energy of the beam, for example. So I wouldn't, I don't think it will really help you out. And there are various other problems with it. The one place that does occur to one where such trapping may be useful and practical is transmission of power over some distance. You see, these light beams are powerful enough to sustain a moderate flow of power on a constant basis, at the moment, not more than about 1 kilowatt, but that's a reasonable, useful amount of power. On a pulse basis, it goes enormous powers. Now, it would be useful in certain kinds of cases, such as for powering a satellite, say, to focus the light in the beam and send it some distance, receive the energy with a reflector of some kind. If one could send power over long distances through, let's say, a pipe or something like this without its hitting the surface, then you might think of power transmission, wireless power transmission, in a rather more general way. And if the beam can go through the pipe, but trapped in the center of the pipe due to the gas, trapping in the gas, it'll never get diffracted, never touch the edges and so on, and you could have very little loss. Once we can generate something like 100 kilowatts, I believe, is about what is required to get self-trapping in gas. We can generate 100 kilowatts constantly, then I think this might be sensible to try. Yes?
It's my understanding that high-energy photons can cause the decomposition of a nucleus. For example, in astrophysical consideration, the decomposition of an iron-3 nucleus in certain stars. I realize that you're speaking of much lower frequencies here, but can you show any interaction of laser photons with nuclei?
The simple answer to that is no. You can't produce any internal disturbances within the nucleus, which is, I guess, what you're interested in. You could move the nucleus from one place to another, but that's not highly interesting. So you really can't do nuclear physics by direct action. You can, however, with these laser beams, interacting with high-energy electrons, produce very interesting amounts of polarized and pure high-energy photons, which then can be used for interesting nuclear studies. Yes?
What do you say for the carbon dioxide laser from the 500 power?
The carbon dioxide laser is an interesting laser involving electrical discharge and carbon dioxide gas and some other things mixed with it. It's interesting in putting out a large amount of CW constant power, up to something like kilowatt at the moment. And what uses does it have? Well, I think it'll be a very useful system. For one thing, for communications, which I've just said we're not going to find enormously exciting immediately, and for practical things, but for specialized purposes, yes. But another kind of use is machining, and I think this is not a negligible or unimportant use. The beam is intense enough, so are other laser beams, but this is particularly handy. Intense enough, you focus it, let's say on glass, and you just, you can write this way and etch the glass as you go along and cut the glass, or any material, including very still harder materials, metals. It's being investigated a good deal for this type of purpose. The carbon dioxide beam is in the infrared. It's intense enough it's become really quite dangerous to laboratory work, because you just flick your hand through it and it can go through your hand quicker than you can move it if it's focused a little bit. And being invisible, it's a little tricky to know when it's there and when it isn't. So it's one of I would say the most dangerous type of laser so far as accident is concerned. I think it will be a very useful system. I think another kind of application for it that'll be interesting is radar-like things, because that particular wavelength of 10 microns goes through the atmosphere. It can be very easily and directly focused. It can have quite long range. It's not so hard to detect. I think radar-like applications will be a very natural type of thing. Plus, of course, a number of other sorts of military things for night vision, maybe, and so on. Yes?
Is it possible to produce sonic waves in the audible range?
Yes, but I would say not in a terribly interesting way. These beams which I'm talking about, of course, last only 10 to the minus 8 seconds. So the whole thing is over before a sonic wave has time to make one oscillation. Now, of course, however, they'll produce explosions. You can hear a big bang. The usual way to describe it, as every child knows, is a zap. And so it produces sonic waves. But there's so many other ways of producing sonic waves. I think the real strength of these is to produce very high frequency waves, and they can go up to frequencies rather higher than we've been able to generate by other methods, and furthermore produce these frequencies inside of almost any material, so allow us to study their propagation inside of even the most lossy materials. These very high frequencies are difficult to generate, so I think that's greatest value in terms of study of acoustic waves, a very high frequency range rather than a low frequency range. They'll produce them, but we have easier.